Hi, my name is Shahnaz. In last lecture, we were discussing the ways of constructing new categories from the old categories. So, one of the ways is to use the principle of duality, in which we construct the dual of a dual or opposite category of a given category. So, if we have, say, a category A, which contain the class of object, the morphisms between object, the identity morphisms on object, and the composition of them. The opposite category consists of the same class of object, but these morphisms they get reversed. So we write OP to emphasize that the arrows are reversed. So the identity remains as it is, and this composition is also reversed. So write OP here. So this is one of the ways of constructing a category, new category from a given category. And there is another way that is called the construction tool. So here we are given two categories and we define their product. So let say A and B be two categories. Then the product of A and B is the category. We denote it by category A times category B, in which the class of objects, I mean the object class of the category A times B is actually the object class of category A times the object class of category B. So this is uh, mm, I mean this is the class of objects and the morphisms of this new category. So the home of category A times B. So this stands for that we are talking of morphisms between the objects of this new category. So here the object is a pair. So we write A comma B, A prime B, A prime B prime. So a morphisms between these two objects of this new category A times B is actually the morphism, I mean the amorphism. I mean when we consider A and A prime, I mean the objects of the category A, then this is the class of morphisms in the category A times the morphisms between the objects B and B prime in category B. So put another way, an object of category, I mean, so if we put it in another way, so an object of the category is A times B is a pair A comma B. So the objects of this category look like these pairs, where the first component A is an object in category A and B is an object in the category B. So where this A is an object in category A and this B is an object in category B. Similarly, a map between two objects, say A, B, and to A prime, B prime. So, I mean, this is a map in the category A times B. So this is actually a pair F comma G, where F is a morphism between the objects A and A prime in category A, and this G is a morphism between objects B and B prime in category B. So this this gives us a new category. So this category is constructed using the categories A and B. Now we have a proposition here. It's a small proposition, short result. So suppose we are given two morphisms. Say, so if F is a morphism from object A to B, and G and HB morphisms from object B to A. So they are morphisms such that if we compose the maps, say G and F, so if this is the IND morphism on A, and say F composite H is the INT morphism on B, then the morphisms G and H are equal. So then G and H are equal. So let us prove this. So we are given like this. So we have, say, we have object A here, we have object B here. Between A to B we have a morphism F. Now from B to A we have two morphisms. One is the morphism, say this is the morphism, say G, and this is the morphism, say H. So we are given that if we compose uh, F with G, F followed by G, we have INT on A, and if we compose H followed by F, we have INT on B, then this G and H, they are actually the same morphism. So we have G composite F. So G composite F is a map from F is a morphism from A to A. So we are given that this is the INT morphism on A. So here we have the INT morphism. So this is the morphism F, and this is the INT morphism. Sorry, not F. This is INT on A. This is INT on B. And F composite H is the INT on B. So we have to prove this G and H, they are equal. Now let us start with H. So now we can write H as INT morphism on B followed by H. So this is a morphism from B to A, because first we have go via IB 1B, which is a map from B to B, then followed by H, which is a map from B to A. So the resultant map will be a map from B to A. So by definition, these two maps are equal. So this is same as H composite. Now identity on B is same as F composite H. Since category respect is the associativity of this composition, so we have, so this is equal to H composite F. Sorry, this is F here. This is uh, I think this is yeah, this is H here. So H is same as, oh, actually H is given like this, so I'm sorry. So actually H is given like this, so we have identity on A followed by H. So identity on A is a map from, so first we have to go via H. So this is the map from B to A. Then we have to follow the map identity on A, which is a map from A to A. So the resultant map will be a map from B to A. So now this is equal, identity on A is actually G composite F composite H. Now using the properties of a category, so this is equal G composite F composite H. So this is same as, now G composite, so this is G composite F composite H is actually identity on B. Now again using the properties of a category, so this is the map G. So this proves that the map G and H are equal. Now with the help of this result, we can show that if F is an isomorphism, then its inverse is unique. Now let us recall what do we mean by an isomorphism. So if we have object A and an object B and F is a morphism from A to B, then we call this map F to be an isomorphism if there is a map G from B to A such that F composite with G is the identity on B, uh, and G composite with H is, sorry, F is the identity map on A. Then in such case we call G, I mean F to be an isomorphism. Now, and we call this G to be the inverse of F. Now, if F is an isomorphism, with the help of this result, we can prove that its inverse is unique. So we have a corollary, and this states that if G1 and say G2 are inverses of a morphism, say F, then these morphisms G1 and G2 are actually the same morphism. So to prove this, so the situation here is like this. So we have say object A, object B, between A to B we had a morphism say F, and we claim that G1 and G2 are its two inverses. So if G1 and G2 are inverses of F, then, so note here we have from A to A, which is the identity on A, and from B to B we have the identity on B. So then, now G1 and G2 being inverses of F, we have G1 composite F. So this will be actually an identity, the identity morphism on A, and F composite with G2 is identity morphism on B. So now using above result, we can directly see that G1 and G2 are equal. So then, because this, I mean this satisfies all the hypotheses of the above result. So then, using above result, we see that this G1 is actually equal to G2. Now, from this corollary, we saw, I mean, one can see that the inverse homomorphism F is unique. And so let us write this down. So from this corollary, one can see that the inverse of a morphism, say f, is unique, and we write its inverse by f inverse. Now we have one more result here. Suppose if we have a morphism, say f from A to B, this is an isomorphism. Then we claim its inverse is also an isomorphism. And the inverse of f inverse is f itself. So let us call this item first, and item second is that let us go to the next page. So we have item second here. So it says that if f is a morphism from A to B and G is a morphism from B to C. So suppose they are both isomorphisms. Then so is there then the composite map. So we can define the map G composite F, which is a map from A to C. So this A to C, this morphism is also an isomorphism. And then is also an isomorphism. And the inverse of this composite map is the composition of F inverse with G inverse. Let us prove the item first. So one can note that, so since F from A to B is an isomorphism, its inverse, so it is inverse, F inverse is unique. Now to prove F inverse is also an isomorphism, what we have to prove? So let us first recall what do we mean by an isomorphism. So we call a map F from object A to B an isomorphism if there exists a map G from B to A such that G composite F is identity on A and F composite G is identity on B. So here F is an isomorphism and it is inverse, F inverse is unique. Now to prove F inverse is isomorphism, we have to prove these two conditions. So note that if we first do this composition, F composite F inverse, so this is the identity map on B because F inverse is given to be the inverse of F and F inverse composite F is identity on A. Then by definition F inverse is also an isomorphism and it is inverse, it is inverse, which is the inverse of F inverse is same as F. So it follows from these two expressions. Now for the item second we have, so since f from A to B and G from B to C are isomorphisms, so then they must have inverses. So let F inverse, which is a map from B to A, and G inverse, which is a map from C to B, be their inverses respectively. Now, to prove the composite map GOF is, uh, I mean, isomorphism, we have, so now G composite F, so we claim its inverse is the map F inverse composite with G inverse. So then this is equal to G composite F inverse composite G inverse. So this is same as G composite. Now F composite F inverse is actually the map identity on B composite in G inverse. Now if we look at this map, this is the map G itself. So this is G composite G inverse. So G composite G, since G is the inverse of G, that means G composite G inverse will be the identity map on C. So this is the identity on C. Also, uh, F inverse composite G inverse composite G composite F. So this is by definition. So this F inverse composite G inverse composite G composite F. So this is same as F inverse. Now G inverse composite G is the identity map on B composite F. Now this map is F inverse itself, or this map is, I mean this map is F itself. So this is equal F inverse composite F. Now F inverse composite F is the identity map on A. So that means uh, the map F inverse G inverse is the inverse of G composite F. So this shows that the composite map GOF, which is a map from A to C, is an isomorphism. And the inverse of, I mean, this is an isomorphism with inverse F inverse composite G inverse. That is the inverse of the map G composite F is the map F inverse composite G inverse. Now we are going to define the product of two objects in a category. So we have the definition. So let us consider a category. So let this fancy A be a category, and suppose A and B belong to the category A. I mean A and B are the objects. Yeah. Now a product of AB, a product of A and B, I mean these two objects. So this is an object which we denote by A times B. But this object is equipped with a projection. I mean equipped with projections. I mean we have two projections from the object A times B to object A, and object B. Now this is the projection to the first component, that is known by this by P, and that is known this is by Q. Now we call this A cross B the product of A and B such that for all maps for all maps F from object some object, say C to A and G from C to B. So C is some object, and these F and G are morphisms from that object A and B respectively, such that there exists a unique morphism which we denote by F and G, such that P composite with this morphism F comma G is the map F, and Q composite with the morphism F and G is a morphism Q. This means, or put it another way, uh, uh, we have that is the diagram. Now, what is the diagram? So first we write the object C here, and we write the object A cross B. So we claim here that there is a morphism F and G. So actually this morphism is from object C to A cross B, such that, so this is there's a morphism from object C to object A cross B, which we denote by uh, F comma G. And from A cross B to A, we have the morphism P. From A cross B to B, we have the morphism Q. Now for C to A, we are given the morphism F, sorry, yes, F, and from C to B, we have the morphism G. So that means that is so this these two lines here says that this diagram commutes. So that is the diagram commutes. Now, keeping this definition in mind, we had the following proposition. So, I mean, this proposition says that the product of two objects in a category is unique up to isomorphism. So, the product of two objects in a category is unique up to isomorphism, up to an isomorphism. That is, if suppose we have two, I mean, we have object A, we have object B, and suppose D and D prime are the products of A and B. Let us call this PQ, and let us say this D prime. Let's call this P prime. Let's call this Q prime. So if D and D prime are two products of the objects A and B, so they are products of A and B. So what we have to prove? Then we have to prove D and D prime are isomorphic. So then there exists a unique isomorphism, say K, from D to D prime such that Q prime K is same as Q and P prime K is same as P. Let us prove this. Now, what do we assume? We assume D and D prime are two products, the products of A and B. And then we use the definition of product. So since D and D prime are products of A and B, then we have the following uh, commutative diagrams. So when we assume that D prime is the product of A and B, then for any C, so in particular, if we take C, for C, if we take D, then from D to D prime, let us call this map K. From D to, let us, so from D prime to A, we have the map P prime, and from D prime to B, we have the map uh, Q prime. So let us keep this in mind. So let us go to the previous page. So what is the definition of product? So we say if C is any object, then from this object to object A cross B, we have this unique morphism such that this diagram commutes. Now we are given, from C to A, we are from C to M, C to B, we are given the maps F and G. So in place of C, we take D and we assume D prime is a product. And in place of C, we put D. So from D to A, we are given two morphisms. The morphism P, and from D to B, we have the map Q. Similarly, we can switch the roles of D and D prime. In place of C, we can take the D prime, and we can assume that D is the product of A and B, and then we have the map here. Say let us call this K prime. From D to A, we have the map P. From D to B, we have the map Q, and from D prime to A, we have the map P prime, and D prime to B, we have the map Q prime. So these two diagrams are commutative. That is uh, P prime composite with K is P, and Q prime composite with K is Q. And from this diagram we have P prime composite with K prime is P prime, and uh, this is the map Q here. Q composite K prime is the map Q prime. So this is what we are given. So we claim, so what we had to prove? We had to prove D and D prime are isomorphic. So for that we want to prove this K and K prime are both isomorphism, and K is the inverse of K prime, or K prime is the inverse of K. So we claim that K prime is the inverse of K. Now to prove this, we have, so we have P prime. So if we look at the map P prime composite, so P prime composite K composite K prime. we get the map P prime composite K prime. Now P prime composite K is the map P. So this is composite K prime. Now P composite K prime is the map P prime. Similarly, Q prime composite with K composite K prime. We get the map Q prime composite K prime. Now Q prime composite K is the map Q here. So we get the map, so this is K prime here. We get the map Q composite K prime. Now Q composite K prime is the map Q here. Now let us, what these two expressions say here. These two say that the diagram commutes. So we have the map, we have D prime here, we have D prime here. Now the map K composite K prime is the map between D and D prime, because from D prime to D we have the map K prime, from D to D prime we have the map K. So K composite K prime is the map between D prime and D. So this is the K prime composite, sorry, K composite K prime. And here we have the map P prime, we have the map Q prime, and this is the map P prime, this is the map, so this is object A, this is object B, this is the map Q prime. So what we proved here, we proved K composite K prime composite P prime, which is the map this P prime, these two arrows composite is this map. So we prove this composition is this map, and this composition is this map. So this means that this diagram commutes. So one can write here, hence the diagram commutes. Now, if this diagram commutes, then we have, by definition of the product, we have, so but by definition of product, between D prime to D prime there is a unique isomorphism, but we know that there is also the identity isomorphism. So that means K composite K prime has to be the identity morphism. So by definition of product, there is a unique isomorphism from D prime to D prime. That makes this diagram commutative. That makes the above diagram commute. But we know that the INT isomorphism also makes this diagram commute. That means this K composite K prime has to be equal to the INT morphism, because K composite K prime makes this diagram commutative as well. So hence K composite K prime is the identity morphism on D prime. Similarly, by taking the map K prime composite K, we can prove. So similarly, we can show that K prime composite K is the identity map on D. So now if this is the case, that means K is an isomorphism with inverse K prime. So that means D and D prime are same. So hence K is an isomorphism. That means this D and D prime, they are isomorphic. This proves that the product of two objects is unique up to the isomorphism.